Medurstand. Understanding medicine.
I am Professor Aziz-ur-Rehman, and today we are going to start with the endocrine system, and today's lecture consists of just introduction to endocrinology. Endocrine system is of three types. One is pituitary dependent. We all know that pituitary gland is master gland. It controls many other glands through its hormones. Now examples are uh, thyroid gland, adrenal glands, and gonads. Now, these three glands are under the control of pituitary and they work constantly under the command of pituitary gland. Then we have a pituitary independent system. Now, again, there are some glands which work independent of the pituitary command, but they have their own feedback loop system. Examples are pancreas and parathyroid glands. So these are two main examples. But then we have many miscellaneous endocrine tissues all over the body. There are some scattered cells which have endocrine functions. They may not have a tissue like one gland, but they are dispersed all over the body. They exactly work like an endocrine tissue. So collectively, they could be called endocrine glands, but they are not just one organ. So we are going to take them up individually and discuss them in some detail. Now, first of all, the most important, the pituitary dependent endocrine glands. So little introduction here. This is hypothalamus. Hypothalamus is actually endocrine tissue as well as brain tissue. It provides connection between endocrine system and the brain. We all believe that ultimately everything is controlled by the brain. So brain affects our endocrine system through hypothalamus. This is the hypothalamus, and there are various nuclei which produce secretory hormones and also inhibitory hormones. And then there are certain collection of neurons which produce actual hormones which are secreted into the posterior pituitary. Now, these secretory or inhibitory factors or hormones are produced by these nuclei, these neurons. They go to this portal system. The pituitary gland has a unique portal system. This is the portal system, arterial blood coming and passing through the lower part of the hypothalamus, carrying along all those stimulatory and inhibitory factors. Now they then go to the anterior pituitary. Anterior pituitary consists of various types of cells. All cells are specialized to produce a different type of hormones. Now these factors, they will either stimulate or will inhibit these specific hormones, and they will then in turn control other glands. So I think this is very delicate system. Then in the posterior pituitary does not secrete any hormones. It does not produce any hormone. It only collects the hormone which is produced by the hypothalamus. It just is collected here and then released into the circulation whenever needed and in just the amount that is needed. So this is the pituitary dependent endocrine gland system. One very important component of this is feedback mechanism. Now, I think I always consider this feedback mechanism is one of the most intelligent mechanism which exists in the nature. This is perhaps the basis of our survival. If there was no feedback system, then perhaps life would not be possible. Now, what we mean by feedback mechanism is this is a regulator hormone. In our case, it is pituitary. Now, pituitary will produce certain substance which will stimulate the target gland. Let's take the example of thyroid or adrenal or gonads. So this regulator hormone, the pituitary hormone, produces some substance which has stimulatory effect on the target gland. So target gland will produce that hormone, and to keep that hormone in the right level, it has got the inhibitory effect on the regulatory gland. Now, for example, if you take the example of this thyroid, uh, pituitary will produce TSH. TSH will stimulate thyroid gland. Thyroid gland in return will produce T4 and T3. Now, once there is enough level of T4 and T3 in the body, it will start sending inhibitory signal to the pituitary to tell the pituitary that there should be no more TSH because there is already enough T4 and T3 in the body. Just the opposite will happen if there is deficiency of T3 and T4. This inhibitory effect will be lost and the pituitary will start producing too much TSH as an attempt to produce T4 and T3. So this feedback mechanism is the basis of endocrinology, and it also is important to understand many abnormalities in endocrine diseases. Now, regulation of pituitary hormones. Now, this is actually the picture. You can see this is the representation of neurons which produce various releasing hormones and inhibitory factors. Every cell is specialized to produce a specific inhibitory or stimulatory factor. They go to the anterior pituitary through the portal circulation. Then all these releasing hormones and inhibitory factors, they have specific targets. There are specialized cells. Some are specialized to produce growth hormone. Some are specialized to produce LH and FSH, luteinizing hormone and follicle stimulating hormone. Some cells are specialized to produce ACTH, adrenocorticotropic hormone. Some are specialized to produce thyrotropin or thyroid stimulating hormone, and some are specialized to produce prolactin. So all these cells, they produce various hormones. These three I have circled because these three hormones do not have any direct action on the tissues. They work through another target gland. This FSH and LH will work through the gonads, testes in men, and ovaries in women. ACTH will work through the adrenal gland, especially the adrenal cortex, and TSH will work through the thyroid gland. And then those hormones which are produced by the target, they have effect on the tissues. Whereas growth hormone work on the liver, it may have some direct effect on the bone and the tissues, but growth hormone primarily stimulates liver to produce insulin-like factor, insulin-like growth factor 1, which then leads to growth of the tissues. Similarly, prolactin is produced by the cells. This prolactin has effects on the mammary gland and in the uterus. So these are relatively conditional hormones. In the posterior pituitary does not synthesize any hormone. It just stores the hormone which are produced by the hypothalamus, but at the time of need it is released. And the examples of antidiuretic hormone, which regulates our water, very, very essential. Deficiency of ADH could lead to diabetes insipidus, and excess of it can lead to syndrome of inappropriate ADH secretion. And then we have oxytocin. Oxytocin is again a conditional hormone required only in women at the time of parturition. So this is the basic of, and this is the again feedback mechanism. Whenever a specific amount of target hormone is produced, testosterone or glucocorticoid or thyroxine, they would have inhibitory effect both on the pituitary as well as on the hypothalamus. So this feedback mechanism keeps all these hormones in the specific range which is required for our body mechanism. Now, some of the example of pituitary dependent system, feedback mechanism, and hormone regulation. This is gonadotropin releasing hormone. Gonadotropin releasing hormone is produced by the hypothalamus. It stimulates specific cell in the anterior pituitary to produce FSH and LH, they are collectively called gonadotropins, and these gonadotropins do not have any direct action on the tissues, but they stimulate our gonads to produce testosterone, mostly in men, and estrogen, both in men and women, but mostly in women. And this is then, these are the hormones which actually have effect on the tissues. Second example is corticotropin releasing hormone produced by the hypothalamus, and it would stimulate the anterior pituitary to produce ACTH, which is corticotropin. Also, there are the two names, ACTH or corticotropin. This itself does not have effect on the tissues, but it will stimulate our adrenal cortex to produce cortisol and DHEA, especially in women. So these two hormones, they have very, very vital action in the body, and the ACTH itself does not have any action other than controlling adrenals to secrete cortisol. The third example is thyrotropin releasing hormone produced by the hypothalamus. It would stimulate specific cell in the anterior pituitary to produce thyrotropin or TSH, thyroid stimulating hormone, and this will then stimulate cells in the thyroid gland. It will also increase synthesis, storage, and release of thyroxine in two forms. T4 is the main form, which is formed by the thyroid tissue, is released into the circulation. Some T3 is also formed, but most of the T3 circulating in the peripheral tissue is actually converted from the peripheral T4. So these are examples of three pituitary dependent endocrine systems. Now this is the stimulatory mechanism. This plus mean they stimulate this one, stimulate this one, and then this one stimulate this one. So all the stimulatory arm, but then we have the inhibitory arm, just the reverse. Once there is enough testosterone or estrogen, it would inhibit, this is depicted by the negative sign, it would inhibit production of FSH and LH and also the production of G and RH. And similarly, once there is enough cortisol, that would inhibit ACTH and then CRH. Ultimately, T4 and T3 would inhibit TSH and also TRH. So this way, through stimulatory mechanism, stimulating the production, and then once the hormone level is adequate, they start inhibiting. This process goes on, and every minute I think the balance of stimulation and inhibition changes because we need different levels of hormones at various times. Now we're done with this pituitary dependent endocrine gland. We are just discussing the basics at this time. We will take up all these conditions in greater detail in subsequent lectures. Now let's take this one, pituitary independent endocrine glands. There are various examples. For example, PTH and calcitonin. PTH is produced by the four parathyroid hormones, glands, four parathyroid glands which are situated behind the thyroid gland. And they are four, but they function as one. There may be sometimes more than four, but they are typically four. They function as one endocrine gland. And then calcitonin, that comes from the thyroid gland itself. Both these are meant to regulate our calcium, phosphate, alkaline phosphatase, vitamin D mechanism. So they would stimulate vitamin D, all aspects of vitamin D, the absorption of vitamin D from the gut, activation of vitamin D in the liver, and then activation of vitamin D in the kidney is all regulated by the PTH and calcitonin. Then there is effect of the vitamin D regulates our calcium and phosphate. Effect of vitamin D is to increase the level of calcium no matter what it requires. For example, vitamin D will stimulate absorption of calcium from the gut. It will also mobilize calcium from the bone, and it will also prevent excretion of calcium from the kidney. So from all mechanisms, it tries to maintain calcium level above a certain level. It has, generally speaking, opposite effect on the phosphate, especially on the kidneys. So this parathormone and calcitonin through vitamin D, they control our calcium and phosphate. Parathormone is generally stimulatory for the calcium, and calcitonin is just the opposite. And in subsequent lecture, we will discuss how these two hormones work in harmony to maintain our calcium level in a very, very physiological range. The second example is aldosterone. Aldosterone is also a hormone produced by the adrenal cortex. It is independent of pituitary mostly, but it has got its own controlling feedback mechanism. It controls our sodium and water. The effect of aldosterone is to retain sodium and water in the body, and the deficiency would lead to the deficiency of these two. So once sodium and water is maintained, that would have effect on the renin. For example, if we are deficient in sodium and water, it will stimulate the production of renin, and renin will then stimulate the production of aldosterone. If we have too much of sodium and water, it will inhibit renin, and then renin will further inhibit aldosterone. So I think this is very, very important feedback mechanism which is independent of pituitary. And the third one is insulin and glucagon. These two hormones, just like PTH and calcitonin, these two hormones, they work against each other but in harmony to maintain our glucose in a very normal physiological range. Basically, glucose comes from the gut, and we actually take too much carbohydrates and we absorb that, and in the form of glucose. Glucose level rises. Once glucose level rises, it will inhibit the insulin production. Once glucose level rises, it will stimulate the production of insulin so that glucose is disposed of into the tissues. And I think this will definitely be discussed in much greater detail when we take up diabetes. But just understand at this level that insulin and glucagon, they have opposite effect on glucose. Insulin always tries to lower the glucose, and glucagon always tries to raise the glucose whenever required. So both working together in harmony keep the glucose in the normal range. Liver also has a very important role to play in this mechanism, because in the fed state, it is the glucose which is coming from the gut. But in the fasting state, we need glucose, because we can't survive, especially our brain cannot survive without glucose even for a minute. So this glucose, when we have not eaten, glucose is coming from the liver, and liver is producing glucose and releasing glucose from glycogen, and is converting glucose from amino acids and fatty acids. So then they will have inhibitory or stimulatory effect on glucagon as appropriate. So I think the examples, I have given you the three examples how these pituitary independent endocrine systems work. They have their own loop back feedback system. Now let's take the example of the third, the miscellaneous endocrine tissues. There are various tissues, fat for example, fat in the subcutaneous tissue again is mostly our storage place, but it is metabolically active. Much more metabolically active is our visceral fat. It produces leptin. Now leptin is a hormone which controls our weight through our food intake, through our appetite regulation. Adiponectin is another friendly hormone which is produced by the fat tissue, especially the visceral fat, which has got very useful function in the body. Then we have GIT. GIT is also a big endocrine tissue. For example, ghrelin and gastrin. These two hormones are produced by the stomach, and they basically are stimulatory for the appetite. And now when we are very, very hungry, we feel hunger pangs. It is usually mediated by the ghrelin and gastrin. And at the same time, we have GLP-1, glucagon like peptide 1 and GAP also, and YY peptides. These are usually the anorexogenic hormones. They tell our brain that we have eaten enough. They are released at the end of our food intake, and then they tell us tell our brain that we have eaten enough and stimulate the satiety. Then kidneys, again an endocrine tissue. We know kidney as an excretory organ, but it has got endocrine function also. The two examples, it produces erythropoietin in response to hypoxia. Erythropoietin is extremely important for hematopoiesis, for the red cell production, and we know that in many patients with chronic renal disease, erythropoietin level is reduced. And once erythropoietin level is reduced, although the bone marrow otherwise may be healthy, but there may be anemia. This anemia is typically normochromic normocytic, and one of the treatments of anemia in chronic renal disease is administration of erythropoietin. Now we have now genetically engineered erythropoietin, which is given for anemia of chronic disease. Then kidney also produces 125 vitamin D or 125 dihydroxycholecalciferol. So this is an active form of vitamin D. Vitamin D which we ingest in the food or the vitamin D which is produced in the skin is not active. It has to pass through two different activation processes, and only then we have active vitamin D. So we also know that in chronic renal disease with vitamin D is deficient, now we have to give active vitamin D in these cases also to prevent secondary hyperparathyroidism and bone disease. Then heart is basically our engine, our pump, but it is also endocrine tissue. It produces atrial natriuretic peptide, and atrial of course means that it comes from the atrium. It is released in the situation of hypotension, and that is like a compensating mechanism. Atrial natriuretic peptide is very important hormone. It is also raised in heart failure. Now B type, this used to be called brain natriuretic peptide because initially it was thought that it comes from the brain. Now we know it comes from the ventricles. So, but we have retained the name of B. It is called B type. ANP and BNP. B originally was derived from brain, but now we know it comes from the heart. So it is also heart hormone. So these four, in fact, the more also, like skin can also be counted as an endocrine because it produces vitamin D. So there are endocrine tissues dispersed all over the body and they work as one. Now again, we are just discussing the basics of endocrinology, the introduction. Whenever we suspect some endocrine disease, we have two types of tests. Now generally speaking, in endocrinology, either there could be excess of a hormone, which is usually due to some autonomous tissue, maybe adenoma, or there may be deficiency of an endocrine tissue, endocrine hormone. That is usually destruction of the gland due to whatever disease process like autoimmune diseases, infectious disorders, trauma, and malignancies. Tests are generally speaking of two types. We will of course discuss individual tests in different diseases, but two main types I will just, the one is directed toward the hormone levels themselves. We can have hormone assays. For example, if we suspect hypogonadism, we may measure testosterone or estrogen. If we suspect hypothyroidism, we may measure T4 and T3. So this is one way. Then is suppression tests. These tests are generally much more sensitive than hormone assays, and suppression tests are done when there is hypersecretion, hyperthyroidism, hypercortisolism, like that. So when we think that the hypersecretion is pathological, we try to suppress it with some stimulus. We know what suppresses a gland, what stimulates. So we choose some agent which suppresses that gland. If after administration of that hormone, if the target hormone is not suppressed, we draw the inference that hypersecretion is pathological, indicating that there is some disease. So this would actually pick up the abnormality before the hormones will go beyond above the normal range. So suppression tests, but they are relatively more tedious, expensive, more demanding, and not widely available. Then we have stimulation tests. Just opposite to this, if we suspect Addison disease, for example, if any organ, any endocrine tissue is not working properly, is not performing well, is underperforming, we try to stimulate it just to see that if the deficiency of that particular hormone is appropriate under the physiological circumstances, or the gland is not capable of producing. So after stimulation, in this case, in Addison disease, if we give ACTH, ACTH should normally stimulate adrenal cortex and in response should produce cortisol. But if after ACTH cortisol is not produced, that would mean that the adrenal glands are basically damaged. Now this test would be, again, it will show the disease before the cortisol level drops below normal range. Metabolites, sometimes we just check the not the hormone itself, but its metabolites. So I think, like in case of growth hormone, the growth hormone is difficult to measure because it has got very short half-life. Instead, we measure IGF, insulin-like growth factor 1, because that has got longer half-life. So this is one group of tests. We go for hormone assays. We do suppression tests in hypersecretory states. We go for stimulation tests for the hyposecretory states, and we do metabolites when hormone assays are not possible. Then we have imaging tests. So there is a whole series of imaging tests. First, of course, is ultrasonography. It is not applicable everywhere. Like, for example, we cannot do ultrasonography pituitary fossa in adults, but it is listed as first because it is very simple, useful, and cheap test, widely available. So in our setting, at least, our first choice of test is ultrasound. Ultrasound can be done on the parathyroid, can be done on the thyroid, can be done on the pancreas, can be done on the adrenals. So any organ can be visualized with ultrasonography. CT scan is more sensitive because it has got better penetration, and MRI is even better. So after ultrasonography, we normally go for CT scan and MRI also to more clearly define the disease process. If it is a tumor, then it gives us better outline of the tumor, because that will help in resection. So these are the imaging tests of first choice. Then we have some other imaging tests which are applied in some specific circumstances. Scintigraphy is an old-fashioned test, but it is still useful. Scintigraphy uses radionucleotide substances. We know that certain substance is taken up by thyroid gland, for example. Now, if we administer that radioactive substance, radioactive iodine in this case, that will be taken up by the thyroid tissue, not only in the thyroid gland and anatomical position. If there is thyroid tissue elsewhere, scintigraphy will pick up that also. So scintigraphy has a role in determining the hypersecretory states, and it has got particular role in identifying the ectopic production of these hormones. For example, ACTH may be produced by a malignant tissue in the chest. PET scan will pick up metabolically active lesions, especially in malignancy, when we want to know the exact extent of the disease, and when we want to know if a particular tissue is metabolically active or not. PET scan is very useful, very expensive though, but in some situation it has got extremely vital role to play. Functional MRI, there's a lot of advancement in MRI. Functional MRI can pick up the functional tissues of endocrine. So I think that is the basic introduction. Thank you very much for viewing this presentation, and I really look forward to see you in my next presentation, and that is going to be on pituitary disorders. Thank you very much and see you again.